Our ignition control modules feature several innovations. The wire bonds in our modules are thicker than the original equipment part by design. If the system is under stress for any reason, these bonds have to carry a higher current than the OE design can handle. This additional stress is usually due to other components degrading over time, like ignition wires or spark plugs or coils. These wire bonds connect the transistors to the circuit board. Our modules also feature advanced ASIC chips. ASIC stands for Application-Specific Integrated Circuit. The ASIC is the black rectangular component, right here, resembling a centipede. It's the brain power of the module. Fast start circuitry. When you rotate the key in a vehicle equipped with our module, the first coil is fired within 1/3 of a crankshaft revolution. Without fast start circuitry, 2 complete revolutions are required to fire the coil. This is a critical advantage during inclement weather. We beat competitors to market with this innovation by many years. Transistors inside modules get very hot. Another feature of our modules is copper heat sinks. We ultrasonically weld copper platforms between transistors and backing plates to transfer this damaging heat away. You can see the copper platforms right here. We've been utilizing copper heat sinks and fast start circuitry since we began manufacturing modules over 30 years ago. This innovation demonstrates advanced manufacturing capabilities. Ever wonder how a manufacturer produces products consistently to the same output levels? If they're doing it right, they're using laser trimming technology like we have for more than 3 decades. Different circuit designs call for specific flow levels, which must be adjusted to very tight tolerances. We manage these flows through 2 applications of laser trimming technology. Here's how we do it. The first level is called passive laser trimming, and it is used during the manufacturing process of the circuit boards themselves. Resistance is measured in the circuit board connections, and where resistance needs to be adjusted, lasers are used to trim precise amounts of the conductive material away. The second level is called active laser trimming and is used on fully assembled modules to precisely set the complete unit's output. The resulting accuracy and consistency means improved performance and reliability. As you can see, there are many advantages to our modules: thicker wire bonds, ASIC chips, copper heat sinks, fast start circuitry, and laser trimming. Advantage: Wells.
Okay, welcome to another live Wells Tech training event. We are so happy you are here. Today we're going to be talking about dual lab scope traces. Remember last time out we were talking about digital signals and what to watch out for that. And this time we're going to combine signals and see how they interact together. That's what dual traces is all about, is making sure both these components are triggering or signaling at the correct time and reacting properly. Okay, so last time out, this time we have a 2007 Pontiac Grand Prix with a 3.8 supercharge in it, and what we're going to do is a relative compression test, and I know we've done this in the past, but we're going to do a little bit different this time, and we're also going to look at the cam and crank sensor signal. Now, what we're going to do with this is we're going to take you step by step from the point of getting your scope out of the box or out of your toolbox, wherever it is, put it on the vehicle, and step by step where to set it to get the result that you're looking for. All right, this is a great class. Don't miss it, and please tell your friends about it. All right. But before we get started, before we go to the cars, we have to talk about, yes, the t-shirt giveaway. Yes, would you like one of these Wells Tech t-shirts? Of course you would. All right, here's the question. Last time out, we were talking about digital signals, right? And a digital signal looks like this. And we were talking about the hash marks that you frequently get on the baselines, whether it's your 5-volt signal or your ground signal, you get this hash marks. And we were talking about what's important to look at. And we called it a rule, all right? What is that rule called? Is it A, catch-22 rule, B, 80-20 rule, C, 14.7 to 1 rule, and D would be the 110 proof rule. All right, which one is that? A, B, C, or D? You know, okay, text that in or in the chat, and first one in with the correct answer will win one of these t-shirts. And email me with your shirt size and your mailing address, and we'll get that out to you right away. All right, with that, we're not in the classroom very long today because it's a hands-on day. We're going to be working on the car, and we'll be doing some cool stuff. So let's get over there and let's do it. I'm taking my coffee. Oh, wait, before we go, I got some news for you. See these things right here? We're always talking about back probes. Go out to AES Wave and buy these back probes. Guess what? They gave us a few sets to give away to you. All right. And so in our next training class, we're going to be giving away a set of back probes. So don't miss it. And by the way, our next training class is on hybrids. Again, on hybrids. Now this is going to be, Jim Bates is going to be here. And he is hybrid certified. He is a hybrid guru. And he's going to show you how to disable some of the hybrid systems and things to watch out for actually working on hybrid. So there you go. Lots of cool stuff coming up. It's a lot of fun. Let's get working on the car. After all, that is the fun stuff. Come on, let's go. All right.
All right.
Hey, Mike.
Hi, Mark.
What do we got here?
Well, right here is our 07 Grand Prix with a 3.8 liter supercharged V6.
Okay, a supercharge. Woo. All right. Mike started working for Wells about 2 months ago. He was in our last presentation for just a little bit, helping us out. But he is a technical services instructor, so he's going to be doing more instructing. And before he came to Wells, he's AC certified master, and also he worked at a Ford dealership, and you did a lot of the electronic work.
Right, yep.
For the dealership. How often did you grab your lab scope?
I didn't grab it that often. If I knew how to use it as well as I do now, I would have been using it almost every day.
Yep, it's too bad they don't teach you that,
right?
Really how to use it. Okay, and that's what we're going to do today, and Mike is going to be doing the instructions, and the reason for this is we're going to take you step by step all the way through the diagnostics, how to set up your scope, step by step. Okay? So there you go, Mike.
All right.
You're there.
All right.
It's working. It's working.
Okay. So we will go ahead and go to our scan tool or our lab scope here. Well, actually, first of all, I just want to say when we're doing our relative compression test here, I went ahead and disabled our fuel pump by pulling our fuel pump relay. When we're doing our relative compression test, we want to make sure that it doesn't start up. We just want to have it cranking over. All right, so we'll go to our lab scope now. And we go ahead and get my leads out. And I'll start with this lead right here.
Notice that they are nicely organized.
Yep, I don't have to untangle them every time I get them out or anything like that.
Right.
So I got my leads here. So I'm gonna go ahead, hook my yellow wire into my channel 1 on the lab scope. And you can see here there's 2 black wires. They both go to ground. One is capped and one is open so that they could be connected with another one. So when we're using 2 channels, we can have both channels using this shared common ground.
Each channel has to be grounded.
Correct.
And you can use a common ground for each.
Yep.
That's very cool.
All right, so then we'll go ahead and I'm going to hook up my ground next. I'm going to get my alligator clip out here. And I'm going to take the other end of my wire here. You see this one's got a black and a yellow lead. I'm going to take the black lead, put my alligator clip on, and I'm going to hook to the engine mount right here on the engine side. So that's a nice sturdy ground there. You could go to your battery or a chassis ground or body ground.
Any known good ground.
Exactly, but you got to make sure that it's a really good ground because the lab scope can be kind of picky when it comes to ground.
Yep.
Then we're going to take our yellow lead, and I've already back probed into my fuel injector. We're going to use our fuel injector as a trigger on this one. We've shown before that we've used the spark plug wire, and we'll actually show that one next. But first we're going to start using a fuel injector as our trigger. So I'm going to go ahead and hook into the control side of our fuel injector here, and what this is the PCM controls this injector by grounding one side of this injector to turn it on. So when the PCM grounds it, the injector's on. The other side is fed power all the time. All right, so that one channel the lab scope's hooked up, so now we can trace our fuel injector. So now we want to get our second channel hooked up. We have this OTC amp clamp here. You can get an amp clamp if you don't have one. You can go over to AES Wave, pick up an amp clamp from them. And we have this nice connector on here. Also you can get from AES Wave. But this connector allows us to hook it up into our lab scope.
That's very, very handy.
Yeah, it's a lot easier than the other.
Normally you'd have to use a banana plug.
Right.
And there's no way to hook another ground on there.
Right.
There is, but it's very difficult.
Right, so yeah, this is real simple. We just hook this into our shared ground that we had, and we hook our red lead here into our channel 2. All right, go ahead, turn our amp clamp on, and I'm just going to clamp this right around our starter, our battery cable going to the starter.
And where did you set that amp clamp?
The amp clamp is just set right up here against the ignition coil, just kind of.
No, I mean,
the setting is turned all the way up. It's set at 1 millivolt, 100 amp rating. All right, so now the amp clamp is going to be reading amperage. But when the amp clamp is reading amperage, it's actually converting it to voltage so that our lab scope can read it. The lab scope is reading the voltage difference, just like a voltmeter would, like your Fluke or whatever you're using, would read voltage. The lab scope is doing that, but instead of a few times a second sampling, this lab scope's sampling at, what, a couple million times a second?
Yep.
So it's a lot quicker. So we'll take our scope over here, and we'll get this set up so you guys can see it on camera. All right, get out of the way here. All right, so we'll go in and back here, we'll go to our 4-channel lab scope.
Okay, that looks good.
And we'll click on this. All right, so as you can see, we have our yellow and green bars right here. And these are just representing both of our channels that we have, our amp clamp here and our injector circuit right here. So why don't you go ahead and crank it over, Mark, and let's see what this looks like.
Here we go.
All right, that looks good. Okay, so right now, our settings on our lab scope, before we even talk about our graph, our settings on our lab scope right now are going to be, we're set right now at 0, our time right here is 0 to 20 seconds. That's the window that we're viewing. We're viewing a 20-second window right now. That's our time interval. And our voltage for our green and yellow wires are about 0 to 5 volts right now. And that's the window that we're seeing right now. So as you look really close here at our yellow wire, you can see that the yellow signal goes up off the top. So the lab scope is reading that voltage reading, but it's off of the scale that we have set right now. So what we have to do is actually kind of zoom out, take a look a little bit further back so we can see where this voltage stops up here at the top. So to do that, we're going to go back to our live view, and we'll bring up our menu. And I'm going to go ahead and I'm going to change this scale. So now I would kind of think that because this injector is getting a 12 volt feed from its fuse, I'm going to go to a 20 volt scale because I'm thinking that it's going to be over 10 volts. So put on a 20 volt scale, hit back, and we'll crank it over again and see how this looks. Okay, so that looks better. All right, so when we're adjusting our lab scope, now we just adjusted the voltage on that single line right there for our channel 1. Now, whenever we're adjusting time, which we're going to do next here, we're we're going to adjust time. Whenever you're adjusting time, it's going to adjust it for both channels or all 3 or all 4 channels, whatever you're using. The time adjustment is for everything. You can adjust voltage individually. All right, so we'll go back to our scope here now, and you can see our spike from when our fuel injector is turning on right here and here, and that's when the PCM is grounding our injector. All right, so now what we want to do is we want to look at where that injector is firing in correlation to where our crankshaft is. But this right here just looks like noise. It's hard to see exactly what that is, so we want to get more in detail on that. So for starters, we're going to go ahead and we're going to zoom in kind of on this line. We want to see more in detail. So right now we are on a 5-volt scale. Let's go ahead and change that scale. Let's change our, oh, we got to go back to live. Let's go ahead and change this scale down to, let's try 2 volts. All right, let's see how that looks, Mark.
Okay.
All right, so now you can see our peaks and our valleys are a lot higher here. You can see them, they're a lot wider. But you can't really tell what's going on side to side because we're in a 20-second window. So now what we want to do, and what we're going to do now is we're going to change our window from the 0 to 20 seconds. We're going to change it down to a lower number. We're going to kind of zoom in on our picture. So we're going to change that down to a lower time setting. When you go lower on time, you see closer. So we're going to change that time setting, and we'll go in here, and we'll change this down to, let's go down to about, oh, we got to go back to live. Let's take this 20 seconds, let's go down to a 2-second window. So now from start to finish, left to right here, it's a 2-second window instead of 20 seconds. All right, go ahead, crank it over again, let's see what we got. All right, that's what we're looking for. You can see really clearly now where our fuel injector is pulsing. Each pulse the fuel injector fires, and you can see really clearly the peaks and the valleys of our compression stroke. When it's up at this peak here, the starter is requiring the highest amount of current, which would symbolize that the engine is on compression stroke. As you look across here, these are all about the same, which would lead me to believe that compression on all 6 cylinders are very, very similar. If you had, say, one cylinder was low on compression, you would notice that one of the peaks there would be lower depending on how low it was on compression. So as we look back at our lab scope now, we can kind of trace where our fuel injector here is firing. We can trace down to where it's firing in relation to where the crankshaft position is. So now this engine's pretty cold. It's probably around 70, 80 degrees. So our injector is actually firing on the beginning of the intake stroke. So here would be compression. So as the intake valve opens, it's firing the injector, and then it starts up onto the compression stroke. If the engine was warm, we would expect to see our fuel injector to be pulsed on a little bit later, more towards the compression side. If the engine was colder, it's more likely that our injector would fire a little sooner. And to get even more accurate with this, we would want to bring our signal down here for our crank, our compression, and we want to bring this up, and we want to just check where the peaks cross. This would be the most accurate way.
Pinpoint then.
Yep, this will pinpoint exactly where it's firing. So
right.
that's a really good test for that.
Yeah, and it is a good test, and a relative compression test is a great test. But let's say we wanted to take a look at the timing chain on this. This isn't really a good way to do it.
Right.
We have to look at the spark, right?
Right. So we want to check spark now. Let's go ahead and get that set up to hook up for spark.
Okay.
So on this engine, it has 3 coil packs, ignition control module, not coil on plugs. So we're going to take our inductive clamp here, and we're going to hook this around one of our spark plug wires. We're going to go on cylinder 1 so that we can see where cylinder 1 fires in relation to where the crankshaft position is. So when we're looking at that, we're going to know when the computer is firing the spark plugs so that we know roughly how our timing is, and then we'll see if it's in spec or if it's not. So let's go ahead and get this hooked up. So first of all, I'm going to disconnect my channel 1, which was my fuel injector. We're not going to be using that anymore. But I am going to keep my ground hooked up because this is a good engine ground and we need to have a ground. So I'm just going to leave that hooked up. So I'm going to take my amp clamp. Again, we have a black and red. So I'm going to hook my black into the ground and just piggyback it in there. And I'm going to hook my red lead into channel 1. And I'm going to take my inductive clamp here and I'm going to put it around cylinder 1 spark plug wire. All right, so let's bring this over now so you guys can see what's going on the screen. Let me get out of the way. All right, so we're still on our old picture, so we'll go back to live. And why don't you crank it over, Mark, and let's see how it looks.
Okay.
All right, that's a nice picture already. So I kind of expected the picture to look nice already because when we went through this, we didn't change anything with our amp clamp at all. Our amp clamp is in the exact same position. So our channel 2 hasn't changed at all. So I had expected channel 2 on the scope to stay exactly the same. So now what we're going to do is we're going to go ahead back to our scope here and we're going to play around with channel 1, which is our spark input. So you can see here we have big spikes here. That's when our spark plug is firing. This is a distributorless ignition system, so it's going to fire the plug twice per revolution. So we can go ahead and bring this down a little bit here, bring our flag down, and as we bring the flag down, you see the voltage changing on the side here. So we're going to bring 0 down. All right, so you can see each of the peaks here, and if you look really, really closely here, you have some really small ones in between the big peaks. Those small peaks are actually picking up, our inductive clamp is actually picking up other cylinders firing. So we don't have to worry about these. All we're really worried about is our large peaks right here where cylinder 1 is actually firing compared to the stroke that it's on. So I'm going to go ahead and I'm going to move up our green bar here so we can get very close to where they cross. And you can see that it's right before, this would be compression. Our spark line is crossing right before top dead center. So our spark plug is igniting just before top dead center.
Which is where it should be.
Right, the engine looks good.
So if we see this, we can be reasonably sure that the internal of this engine is in good shape.
I would agree,
so
yes.
if we got a trouble code, a PO340 or whatever, something concerning cam and crankshaft time,
right.
We can say, all right, we're not going to pull that timing cover off because these results show us we don't have to.
Right, exactly.
That's in good shape.
Yep.
So there's a big time saver right there.
Yeah.
And very important. And that's how you set up your scope to do it, step by step. And I hope you guys are starting to get involved with this and using this because it's going to make you money. It's going to save you time. It's going to make you money.
I mean, this took 10 to 15 minutes explaining it.
And
I could do it faster.
even explaining it, right. If you did it without explaining it, it'd take 5 minutes.
Right. Pulling off
2 guys.
Pulling off a front cover, I mean, that could take hours. You never know.
Oh, yeah.
It could take
Easily.
hours.
Easily.
To come to the same relative conclusion that, hey, our engine's in time.
Let me ask you this. Would a customer rather pay you to take that front cover off, or would they rather pay you to spend 15 minutes on a scope?
I think they'd rather pay to use the scope.
I think so too, and if you're not being paid for diagnostics, you should be paid for that.
Right.
You need to train your customers.
Yep.
Okay.
Just as an example, if our timing was off, we would look in here and our spark line on our scope.
There you go.
There we go. Our spark line on our scope would actually be after top dead center on our compression stroke.
Right.
We would see it over on this side here.
At that point, if we saw it on that other side, what would we do next?
Well, I would say our best bet would be to hook up to our cam and our crank sensor and actually check the correlation.
That's what
on
we're
the
going to do now. We're going to look at the correlation between the cam and the crank sensor as if, why don't you go ahead and set up for that.
All right.
As if we did have a problem with our relative compression. And that way we can verify whether or not the cam and crank are in time. So that's what we're doing right now. While Mike is getting that ready, have we had any? No comments. You guys are awful quiet today. I don't know. We've only given away 1 t-shirt. But anyways, the answer was, I believe it was B, 80-20 rule. Remember, you know, when you're looking at a digital signal, you're not concerned with the very top or the very bottom. You're concerned with 10% in from that. That's the trigger point where the computer says, okay, that's a trigger moment. We're on or we're off at that point. Okay, so keep that in mind. You don't have to worry about those hash marks unless they go dip down or dip up to a point that it's a trigger. Okay.
All right. So
All right, we're all set to go. Good.
while you were talking there, I was just getting our amp clamps out of the way. We're all done using our amp clamps. Now we're going to go ahead and use two of our leads, and we're going to go into cam and crank sensor inputs. On this car, it's actually relatively easy. I went ahead and printed off my wiring diagram, and I looked for cam and crank inputs, and I actually found them going into the ignition control module, cam and crank sensor signals. So I was able to really easily get to the ignition control module on this engine. You can see that it's right here, and I already have it back probed. As you look in there, just to save us a little time, I back probed them already, so I'm going to hook up my leads to both of those. I'm going to take my yellow lead here out of my fuel injector because we're all done with that. And I'm going to go ahead and hook that up to our crank signal here. Get that hooked up. And then I'm going to take my green lead. Again, you got to hook up your ground for your lead. Take that, hook into channel 2, find the other end of our yellow wire here, hook that into channel 1, and get this all hooked in here. And we'll go ahead and get our green wire hooked in to our cam signal. All right. So now we can go ahead and show you guys what it's going to look like for a cam crank correlation. So we're still on our recorded one here. Oh, let me move it over a little. There we go. So I'm going to go back to our live view, and we have a very, very strange pattern here. This looks like our ground's not connected anymore.
That's usually what that means, is that you got a ground problem. So guys, pay attention to that.
I must have bumped it off here.
When you turn it on, you don't have a straight line there. If it's all hashed,
Yep.
it usually means that you have a bad ground. There you go.
So you can see when I disconnect and reconnect the ground how our line goes back, and if I wiggle it on there a lot, we can get a lot of weird interference.
Right.
So you want to make sure that you have a very sturdy, steady ground, and you can tell by our straight line now.
Yep.
You can tell that that's a really good ground now. All right, so we got our ground set. Why don't we go ahead, crank it over, and see what we got. All right, so we have our cam and our crank signal. You can see our cam is green on channel 2, and on channel 1, our crank is yellow. So we can see what's going on here with the crank sensor. We got a lot of up and down here, but we can't really tell what's happening. So what we want to do is we kind of want to zoom in on this crank signal first. We'll start with crank, we'll start with the yellow, and then we'll go to green after. So I'm going to go ahead, go back to live, and now we want to zoom on that one individually. So I'm going to go ahead, change the voltage rating on that. Let's bring that down to 10 volts, because we're going to zoom in, so we're going to bring our voltage down. Okay, why don't you go ahead and crank it over again? Let's see how that looks.
Okay.
All right, that looks good. So now you can see even better the voltage range that that's in. But it still seems like it's too far zoomed away right now. We want to zoom in a little bit more here, and we want to get more in depth to find out what's going on between these ups and downs here. Because this isn't just a solid line, this is up and down, up and down, up and down. So between, what do we got here, about 6.5 volts to 0. So what we want to do now is zoom in our time. We want to bring our time in. And remember, when we adjust time, it's going to adjust both channel A and channel B. So we'll go back to our live view. And I'm going to go ahead, and we're at 2 seconds right now, so 0 to 2 seconds. I'm going to bring that down to 500 milliseconds, so about half a second. So it's now half a second between here and here. So why don't we go ahead, crank it over again, and see what that looks like at half a second interval. Okay. So now you can really tell what this crank sensor is doing with the up and the down, the on and the off. This is what the computer is looking for, on and off between the voltage. On a Hall effect sensor like this one, it's picking up off of our 36-tooth wheel on the crankshaft sensor. So there's going to be 36 teeth in between each single camshaft revolution. But with this view that we have right now, we can't really see our channel B. We can't really, or channel 2. We can't really see what's going on with that. We can't see both signals on here. So we want to get our channel 2 set in here. So let's go ahead and do that now. Go back here, go back to live, and let's change our voltage here. Let's try 10 volts, and let's see how that looks on our screen. So we're going to zoom out a little bit on our voltage. All right, where are we at now, Mark?
Ready?
Yep. Okay, that looks better already. Now you can definitely see that we're at about 7 volts on our cam signal down to 0. So if we lined up these flags here, you would see that they're both about 7 volts to 0. So that looks pretty normal, but I still can't tell where my cam signal is because I can only see one on the screen. So time-wise, we're zoomed in just a little too far. 500 milliseconds between here and here is a little too fast. So I want to change that again. We'll go to 1 second this time. And let's see what it looks like on 1 second. All right. Okay, so when you're doing a cam and crank signal, this pattern that we have up now is about what you're looking for. If you didn't know, you could try and look for a known good. And first we'll go back to the pattern here just so I can show you guys. If you look where a cam signal starts on both of these, you can see, and if I separate them, you can see it even easier. But if you counted between the start of each cam signal, you would have 36 teeth in between, which would lead me to believe the engine's in time. That's what we want to see.
That would be a known good
Right.
signal there.
This would be a known good.
Yeah, we know that this is a good signal because we know this vehicle is running right. There are
Right.
no codes, there are no problems with it, that kind of thing. So we know it's a known good signal.
Right.
And where do you go to find known good signals? How would we verify that that is a good signal?
Right. If I pulled this up and I didn't know what I was looking for, I wouldn't know this bad from good. So you could either go one of two ways. You could either do it the harder way and look up how the cam and the crank sensor works.
Right.
See that the crank's a 36.2, see the cam goes once every revolution.
Right.
So, and then actually time it out and count. But you
Right.
could also go on to IATN and look for a known good signal pattern
Right,
on there.
and that's a good point, and that's one of the things that we do regularly is we go out on IATN looking for known good patterns. We also post patterns out there. In fact, when we get done with this one today, that's what we're going to do because
Right.
we went out on IATN in 07. We looked through a number of different years, but a 3.8 supercharged, there was no known good pattern out there for cam
Right.
and crank. Nothing out there for relative compression either. So
Right.
we're going to post both of these out there. And please, that's what you should be doing too. Remember, we're all in this together.
Yeah.
Right? You know, and we're here to help each other, and we all want to make a living, and we all want happy customers. So that's what it's all about. Let's do it together. I mean, that's
Yeah.
IE10 is out there. It costs you $15 a month to get there, and there's tons of information.
If it saves you time on one job, it's already paid for itself.
It's paid for. Yep. And computer work these days and lab scope work, all that stuff, you got to charge for that stuff. You cannot be giving that stuff away. Your
Right.
time is valuable.
Right.
Okay. Anything else?
I think that just about sums it up.
All right. Good. We got no questions and we have no answers, so we're going to say sayonara. Without you being there, we would not be here. We appreciate you being there. We'll see you again next time in the Wells Tech Garage. All right, let's go test something.
All right, let's do it.
Go have some